Can this be solved by partial sum? Yes, it can. Partial sum is the same as sweep line. Now, why can it be solved by partial sum? Is because I just have L2R queries, right? L2R kind of queries, and I do something of a value, and then I just need the final state of it. I don't need after each. So when I do not need after each, I can just try not to use segment tree. It is an overkill over here. What is partial sum? It is just the sweep line algorithm. At L, we plus something to start its contribution. At R plus 1, we negate it by subtracting it, which means that from L to R, both inclusive, I am contributing that value, something, minus plus whatever it may be, right? So from just L to R, I'm contributing L plus 1, R plus 1, I'm negating that value. Over here I started the plus value, so this will cancel till every index over here, it will do plus. That is just the partial sum. What can we do over here? The main notes would be that what is a meaningful contribution for this problem? It is just that starting from whatever number that I have, first of all I need to change my thought process that every number has to go to 0. I'll try to get every number from 0 iterating from I equal to 0. From here, my I is 0 over here. I'll try to accept no query and then try to go till all the queries, case size of the queries, and try to finish such that my particular every number can be 0, can achieve 0, right? That is my final goal. So to do that, I can just maintain what is a meaningful contribution. Meaningful contribution can come only if, let us take all the cases. Suppose if I is not between L to R, right? This is my L, this is my R, this is my value that it will affect, right? Now for each query, if I say that L to R is the range, and that range has the rightmost pointer which is lesser than my I itself, so it will not contribute to I, right? It will not affect I in any way. We can just go to the next query. Next thing is, if that particular I falls between that L to R range, which means that query will mutate this I. If that query mutates this I also, now we need to consider that. So this is a meaningful thing, right? Meaningful contribution. We have to consider it. Next thing is, if that I is lesser than L to R, then what do we do with that query? Should we keep it as active? Yes. How do we keep it as active? We will consider the sweep line algorithm again, right? We will say that at a later point we are maintaining an array, right? Partial sum array. That partial sum array will keep that context, that for the future if I need it, I'll use it, right? And I'll use its contribution. Right now I don't need its contribution, right? Like I cannot have its contribution. It's not like I cannot like need it, but I cannot have its contribution because it is not falling in the range. But maybe some other number I plus x from here, suppose this number might need it in the future, and that this L might affect me, this L might affect me, this L to R range. So for that we'll just keep it, right? For that, if we see, this is just a pictorial representation of how I can say that what is a meaningful contribution and in what cases. So suppose if Q was here, I was here, and L and R were here, right? Then what is the meaningful contribution? Only this part is the meaningful contribution, right? If the I was between them, then we can say that this much part is the meaningful contribution. This much part was a contribution, but it does not meanify anything because for that particular nums of I, it is not contributing anything, right? Like we don't need it as such, because before this everything has been already done, right? All the I minus x till 0 have already been computed. So even if it is there or not there, we don't care, right? We are at this point, we care about this point. Now the second point to note is, in the particular partial sum expansion, r plus 1 might become a out of bound, right? If we just declare it with n size, so we just keep the partial sum as n plus 1 size, so that it does not go out of bound. Another thing could be that if r is just less than n minus 1, so that maximum of r, right, will become how much? R plus 1 will be, it will become n, right, at max. Like if it was less than r at max, it will become n minus 1 at max, so it will not cross the boundaries. So we can just have that r is less than n minus 1, which would mean that r's maximum value would be n minus 2 and r plus 1's maximum value would be n minus 1, which is well within the bounds if this was not there and it was just partial sum of n comma 0. This is another point that we need to note. Next thing is, in vector initializations or vector construction, right, in C++, it automatically initializes it with the 0 value of that type, whereas the raw C++ int array initialization does not do it. For that we have to manually do initialization for it, right? Next, how do we process the array? So for each number I will check if it is possible or not. For each number, how do I check it is possible or not? When I am at nums of I index, I will check if it is possible to actually, with the k number of queries, whatever index I am at in the query array, right, whatever k index I am at, will that satisfy or not? For that, what I can do is, I can just take a running sum. This sum is a running sum, so it is like a partial sum from the previous one, sweep line kind of a thing. So whatever is the previous contributions which have not ended till now, that will be inside the sum. What will be in this partial sum? This will contain, of index I, will contain whatever in the future, this kind of a thing where we had that I is less than r, right, this kind of a feature. So we just said that the partial sum of L was plus equal to value at that point. So we were just keeping it active for a future time. That future time has now arrived, so we need to consider that particular partial sums value also. Basically what I'm trying to say is, at this point I am at nums I have some partial sum of I which gives me L to R of future contributions, and then I have a sum running which gives me from here whatever had started sum of L's which were contributing. So at this point for nums I, what is the contribution? It will be all the previous contributions which are running till now, which have not ended, and whatever is starting from here, right? So it is sum plus that particular partial sum of I, and then whether this particular thing, right, is lesser than my nums of I or not. If it is lesser than my nums of I, what can I say? That nums of I can be reduced down to 0, because this part is now becoming equal to or greater than, right? When it is equal to or greater than, means that if suppose it was minus 2, right, sum plus that partial sum of something, if it was minus 2, what I can say, that I can maximum bring down that nums of I by 2, right? So if I can bring that this value of 2 by minus 2, that is fine, right? I can get to 0. That is what I want. Now the solution is this. Basically, first I'll have a nums of like the n, right, nums of nums size, and then I'll have a running sum. I'll have two indexes, right? those two indexes can be this answer index only itself. Answer can be the index itself for the queries. Then the second thing is I have initialized with a +1. Now for each of the numbers I will try. For each of the numbers I want to satisfy something, and I will try to satisfy it till the queries are there. Till the queries are there, I'll try to satisfy it. If I have exceeded the query size, then I'll say that okay, we can't do it. But till it is there, I'll just increment that, and then I will try to have the sweep line for these. Now what the sweep line will have, right? If it is a meaningful contribution, include it in the sweep line. So partial sum will include that particular maximum of I comma the L, because as over here we see, right, maximum of this is only the contribution. So even when I, L, R, this was the case, even then the contribution started from L to R only, right? So maximum of this I comma L is where the contribution will start. So this is the contribution start, this is the contribution end as such, and then this is the running sum. So why are doing the running sum is we are just seeing whatever contributions have not ended till now, right? All those contributions we are taking, like how much ever we can take till now. So we are just taking this, and then we are iterating in the while loop for the next value. Let us go to the next answer query if this particular condition is not met, and then we return the answer. So the time complexity will be like order of n plus q size, right? And so another approach to this one also can be like we can do it by a binary search over answer. Why? Because it is a monotonic thing, right? We need from 0 to q size query size with some x, which is the minimum x, which will satisfy such that all the particular numbers can get to 0. We need such x. Now to get that x, we can just iterate over all the queries size from 0 to query size, and then we can just halve it each time, because if some particular x satisfies, I'm pretty sure that x plus 1 will also satisfy it, and it is a monotonic predicate after that. So if at particular x I'm saying at a midpoint that it is satisfying that all the values in my nums can get to 0, right? So even after doing some extra operations also it will get to 0, right? So monotonic predicate is present over there, so we can just search. Now for searching it, it will take an order of log q, right? For searching for that particular x, at max it will take this, and then for each one what I'm saying is I'll check if that can make it to 0. Again, this will use the sweep line algorithm only, or partial sum one, but for each one it will take order of n, so it will become log q into n, but our previous one was n plus m, right? So it just depends, like both are good, but that will have a better linear time complexity. This will have a bit more than linear in the terms of not absolute terms, but in terms of particular first complexities, or else the big O, we can say it will have that kind of an effect. So yeah, this was it. So partial sum, basically two things we need to remember. We need to ask ourselves if a segment tree is required, if after every query it is asking a state for the answer. If not, we can just neglect it. If it just wants the final state, then it is not required. Second, wherever there is a query kind of a thing, we should look into partial sum, prefix sum, or else segment tree, right? Some of this implementation will be there. Next thing is, whenever we go out of bounds, we can either negate it with a particular if condition that only do it if r is like less than n minus 1, so that r plus 1 can maximum be n minus 1, or else we can just have a vector size of n plus 1 and just not consider that of n kind of the array uh, element, because we don't need it anymore, right? We can just pop it if we want, if they are asking the vector as the answer. So these are the things, and one problem can be solved by multiple methods, right? We should go over all the methods, and yeah, that's it. So if you're watching this, if my future self, like I am watching this, uh, I hope I made sense to myself, I guess.